Hello, community. So great that you are back. Hey, we have a new paradox in AI, discovered 2 days ago by UC Berkeley. So let's have fun. I want to give you a 30 seconds introduction. Where is this video located? I already did 2 videos kind of on this topic, and the first one was by the research here by Apple that says here there's an illusion of AI thinking. And then just days ago, a new paper by Georgia Institute of Technology, where it says, hey, multimodal in-context learning is not working at all. Now, the response by the community was interesting, and I show you here just 2 examples. So by Apple, it was easy, no? Everybody more or less said, hey, the only company that cannot figure out AI published here a report about the illusion of AI thinking. So simply, there is no trust by the community into research by a company who is not here commercially, let's say, activating the AI system. And here in Georgia Institute of Technology, and I understand if you are somewhere in the Amazon rainforest or in Bangladesh, you say, hey, this is a school nobody ever heard of, publishing controversial papers. So let's ignore them, because this is not really in the mainstream hype channel. So just let's ignore all this information. And I thought, hey, great. So if it's only about, hey, you have to be an ivory tower institution, the elite university. Hey, today's video is about UC Berkeley, and I hope we both agree UC Berkeley is an outstanding university in the world. And they tell us we have a new paradox, because LLM creates a paradox operating here within vision language model. And you know what? The language model just invents a vision that is not there. Of course, I want to give you an outlook with a solution. But this is given current research and just 2 days old. It's not always easy, but I try my best. And then, of course, tomorrow you will see here video number 4, where I show you that this outlook that we tried to make operative, if we try then to learn or increase the learning for new tasks on this solution, we encounter immediately another problem. And I try to give you also an outlook with also another solution, but please try to understand this is just temporary solution, because what we are facing is AI is just beginning. I know there's a hype about superintelligence and whatever. No, we are just at the ground level. We have so massive problems in our AI systems, and we need open source AI models, because there we can have a deep dive. And I know that current AI models here, either from OpenAI that are completely proprietary, completely closed up, we have no way to access the inner working, or Anthropic, no way to know anything about it. They have massive flaws. And some ask me, but why don't those companies tell us about their flaws? Well, currently they are optimizing their profit margin, of course, for their investors. So why should those companies tell you, hey, we discovered here massive problems in the performance? So we need open source, we need independent university research, like today, UC Berkeley. Let's start. Now, I want this as an introduction for everybody, so I start very easy. Imagine you have a world-class photographer with beautiful eagle eyes here for details, and you have a beautiful narrator. So you ask those 2 here to describe a complex scene. Now, what is happening here is an analogon, but instead of listening now to the photographer and looking what the photographer shows the narrator as visual data, the narrator, our large language model, completely ignores him and makes up a generic and often an incorrect story, because it ignores here the visual information. This is the paradox we're going to talk today. Because this new AI research paper by UC Berkeley argues that many powerful, and of course we have to go with open source, vision language model are failing to make effective use of the rich visual information their own vision encoders provide. So part of the AI system ignores the other part of the AI system. I love this situation because we can learn so much about it. And please understand, it's not a negative. It is just an opportunity to learn and improve. So even though the vision part of the vision language model can see and understand the complex visual details with near perfect accuracy, and we are talking about 80-90%, the language part here of the system seems to ignore this visual information, and this is just pure chaos. And you might say, hey, why should we care? And some of you wrote to me, okay, it's not working. Yes, I don't care. I just wait for the next model. Yeah, but we want to learn. We want to actively understand what are the shortcomings and how can I cope with them today? What is a temporary solution that works? So it is a critical issue for several reasons. Because there is no reliability of vision language model now. It undermines here the trustworthiness for the task requiring here careful observation. Just think about medical image analysis. If you cannot trust that the AI is really seeing here the visual part, what sense does it make to apply AI? Evaluation. We have some standard evaluation protocols and some standard benchmark. Now guess what? This are just giving us a small part of the complete performance of the vision language model. And sometimes what they show us is limited. It leads us to misdiagnose here the problem, and we are trying to fix the wrong component. More about this in seconds. And this kind of research, like UC Berkeley, it forces us to question here the dominant vision language model architecture. Your vision transformer, your projector, your LLM. This plug-and-play approach here of connecting here simply a vision encoder to an LLM is shown to be deeply flawed. But this is something positive because we can improve this, we can build better systems. Now, let's come here to the shocking discovery. UC Berkeley, I went there and, I said, hey, great. So from a group of academic pioneers in 1868 to the free speech movement in 1964, Berkeley is a place where the brightest minds from across the globe come together to explore, ask questions, and improve the world. It is so great. And then I was thinking, hey, wow, there you have here on the official homepage here, a police officer, I hope, and a person in jail. I hope it's not a student. So whatever is going on in the US, I do not understand it at all. But what I do understand is the following. So we have research by UC Berkeley. And you know what? They are relying here on open source model. And interestingly, the best open source model are from China. The QN model I'm going to show you later, they're a really high performance model. And you know what? The Chinese model are open source. We are able to have a deep dive, uncover the layers, really understand what's happening because we have access to the internal workings. No US scientist, elite university or public university, I don't care, why they have no access to a US open AI system. And I mean, with OpenAI, you know which company I'm talking about, that they are now telling us for, I don't know, close to a year that they are going to publish an open source AI model. But just today, Sam told us, hey, it will be delayed further because today we introduce O3 Pro, which even is only for the Pro paying customers and is even thinking longer. So what they do and what they claim to have the intention is absolutely in the opposite direction. So why do we, as US researcher, and I'm sitting here in the heart of Europe, and I'm looking at this and say, without the open Chinese model, that are excellent, by the way, US would have no access to the model, would not be able to understand this model, would not be able to show us the flaws of this model. Those US companies are currently commercializing and get here revenues in billions of dollars. We would trust those models. So it's an absolute fascinating geopolitical configuration how AI research is today in this world. And yes, hey, Europe, we have to do a lot of work, but this would be another video. So let's come to the research. Here we have now the study from UC Berkeley, and the task is simple. You take two images from the same object, 1, 2, and then you ask, hey, can you identify here, if this is now a reference point here on this image, and I moved here just 2 steps further to the other side, Just where's this reference point? No. As you think that in June 2025, an AI system should be able to identify on identical image, just moved a little bit your standpoint, says, hey, yeah, this is exactly the point that you're talking about. Now, how we do this? You know, DINO is here one of the standard tools. And I've shown you here 2 videos on my channel where we're visualizing here the self-attention head of the last layer in a DINO vision transformer. And we had here a Colab notebook. We coded here the visualization of the last layer of the vision transformer and coder stack. And we analyzed here the visual output of each of the 12 attention heads. And we did this here with another one. So if you want to read more or learn more about how we code this, how we do this is the video for you. In general, you can see DINO version 2 here is a self-supervised vision transformer architecture. That is great. DINO stands for distillation with no labels. And now let's do this experiment by Berkeley. So what they say, they say, hey, we just take DINO. No, we just do a pure visual evaluation. So we say, hey, okay, image 1, image 2, which point correspond to each other? And of course, the DINO says, hey, this is the point here, and this is the point in this image. So the similarity for the point C, exactly C to reference here, this is the corresponding point, and this is the correct answer. Great. And you might say, and what? What do you want to tell me now? Now we do the same with a vision language model. And you know what we get? Even if we integrate the DINO as the vision element, we get A. And I would say, wait a minute, A? At the bottom of the image should be corresponding here to the reference point at the top of the image? Yeah, this is what we get out of the model, A. So you see, we have a problem. And to have here a quantification of the problem, Berkeley, give us here this one. So let's have a look here at the accuracy and the result. Let's have it a little bit bigger. So what is happening in our vision language model? If we only take the visual engine out of the VLM and we run it here as a standalone solution, only visual, you see, either we go with DINO version 2, we have 82% accuracy. There are ways to come close to 90%, but never mind. Above 80% accuracy. And you would say, okay, that's acceptable. No? Or if you go with an old clip, we have above 60%. But the moment we put this engine into a vision language model with the current LLMs, the performance falls dramatically under the random chance limit. Here, look at this. DINO version 2 goes under the random chance. I mean, this is unbelievable. It's worse, the performance, than it would be random. What is happening? Now, this is a real problem, and I know that some of you might think, hey, no, this is just a problem. Don't tell me about problems. Show me some beautiful videos about AI-generated content. Hey, wake up. We do have an architectural problem currently in vision language models. I might say, okay, but maybe this is just here for this particular example. So UC Berkeley said, let's check this out for different tasks. Let's go here, semantic correspondence, low-level matching, depth estimation in the image, object affordance, art style, 3D object awareness in the image, and look at the performance. It's always the same visualization. Here, a downward. Whenever we integrate it in a vision language model, the performance breaks down, decreases, crushes. And you see here in the dotted line, this is the random one. So the performance is worse than any random engine at all. Hey, great, this is the state of our vision language model. Would you have known about this? Yeah, those vision-centric tasks, beautiful. Why we do this? What are those elements here that I show you here in this image? Well, they said we pick only vision-centric tasks. This is because we just want to talk about or analyze here the visual characteristic of the inputs. No? We don't want to rely on the language knowledge or the domain expertise of the LLM. We just want to focus what is happening in vision. So they come here from the expressivity of the vision backbone itself. Great, we are focusing on vision. So what is the current status? 5 minutes into the video, we found out that the vision encoder as part of the vision language model performs brilliantly, above 80%, 85%, maybe 90%. Great, it knows the answer. A standalone solution is capable of identifying here the task and giving a solution. The moment we put it into a vision language model, which uses the exact same vision encoder, and this is the crazy part, the performance of the VLM crashes. And I mean really crashes below random guessing. You could go and have a look at your coffee and get maybe a better answer than deploying here a vision language model. How is this possible? Okay, let's analyze this. We want to learn from this. We want to see how the internal workings behave and what is the problem. So the information is there because the vision encoder is part of this system. Yeah? So it is hidden in plain sight. But the vision language model as a total system acts as if it is blind. And this is not what we want for a vision language model. So this here is, let's go with a central mystery. Absolutely. So let's have a look at solutions. When we analyze, when we encounter a problem, we have to find solution. 3 possible solutions. The visual features are corrupt. Yeah? And the problem is here the projector. This is exactly the bridge function between the visual encoder and our large language model. Yeah? There must be something wrong because, it cannot be. So we have now a layer-wise analysis of the LLM performance, and therefore we have to have open source system. We cannot go with an Anthropic system. We cannot go with an OpenAI system that are absolutely closed. We have no access. We cannot learn anything in this AI community. We are dependent what we are given by those companies and they optimize their profit. So guess what? Their interest is on open source learning. Now, UC Berkeley, and I think it's brilliant. It's a beautiful experiment. Huh? And they say, okay, so they perform here visual evaluation, a direct readout from the layers. And not just the initial vision features, but also the vision features after they pass through the projector, and then each subsequent layer of the LLM. This is the power of open source. We can really analyze here each layer configuration and have a look at this. So let's do this. So the verdict is this here, our problem. The verdict is no, not guilty. This is not it. If you look here at the different layers and the accuracy and all the different tests, the performance of the direct readout remains incredibly high throughout the projector in almost all layers of the LLM. So this means the visual information is preserved and remains easily accessible from the vision encoder to the large language model. So it is not the bridge function between those two systems in a vision language model. Damn. But we have a second idea, no? The prompt is bad. Yeah, we know prompt engineering, yeah. So we say, okay, the information is there, no? But now the LLM is not able to understand it, yeah? And since, of course, you will say, hey, rack MCP A to A. No, we just have to optimize the prompt. That's enough. So the model is just confused about the task. It doesn't really understand what to do here with looking at images. So we just have to optimize the instruction to the LLM. We have to do some prompt tuning. UC Berkeley had a beautiful idea. They freeze the entire vision language and introduce a very few prefix embedding so they really can, since it's an open source model, view here the path through the layers and really see what is happening because everything else is frozen. So whatever is learned is now a clear indicator that we understand what's happening. Guess what? The VLM still fails to close the enormous performance gap. This prompt tuning, to the best of our knowledge, provides only a very marginal improvement. Have a look at this at a different task. You see here visually the performance, and if you listen to this on your audio, wherever, this is what you are missing out. Have a look at this graph, this performance graph. And they are not just for DINO 2, they're for Cyclip and Clip, and you see this is not just a particular feature or characteristic. This is a problem that is really at the core of our systems. The core problem is deeper into the vision LLM architecture. And then we have suspect number 3 now. And they say, hey, okay, so if we know that it is not a vision encoder, if we know it is not a bridge function between vision to LLM, so it must be the LLM. No? Somehow the LLM fails to utilize here the vision information at all. No? Okay, so now we do 3 tests, because this is now at the core of the video. So we do a blind test, then based on the finding of the blind test, we will try to train something particular, and then we have a look at the attention visualization activation patterns. So the blind test is as simple as can be. You see, you don't have to be a genius. You know what? You take a blank image. You say, hey, this is an image, absolutely blank. And now you compare this blank image to any other image. And you say now, okay, so let's see what the vision language model is doing now. And if you have a look inside the VLM to see the answer distribution, you see the answer distribution between the absolute blank image and any other real image is absolutely identical. So this means that the vision language model, and here we zoom in on the large language model, the LLM is ignoring the visual input. This is absolutely amazing. So the LLM in the VLM says, you know what? I don't care about the vision information that I get. I'm as a large language model so trained on text only. All my pre-training was on text only. I go with text only. And if there's some channel with visual information coming in, okay, but given my learned behavior, my training, I rather invent something. I rather have, I don't know, some creative amount, but I do not take in the real visual data, which is absolutely crazy behavior, if you ask me. Yeah, here you have the semantic correspondence, low-level matching. Here you see exactly here this particular blind test performed on our visual-centric task. And then we say, okay, let's learn this thing, something. Yeah? So what about fine-tuning? Yeah? I mean, what else? Yeah? So let's say we only have a small budget. So what do we fine-tune the complete model, VLM? Which part of the VLM should we fine-tune? The vision encoder, the projector, or maybe only the LLM? And you know, just a little bit of money, Berkeley, so we use here LoRa to fine-tune now. And we have just an experimental look. What element, if I fine-tune it, has the biggest performance improvement? The result is clear. Fine-tuning the large language model provides you the largest performance gains by a wide margin. This proves again that in a vision language model, the large language model itself is the component whose inability to use the vision is the primary performance bottleneck. And this is amazing. We built a vision language model that is not able to understand or willing to input the visual data that is provided via this bridge function here of a multi-layer perceptron and a 2-layer multi-perceptron to the system. The LLM says, you know what, I ignore you, vision. I'm loving it. You know, new AI research. We need new systems. And then, of course, Berkeley said, okay, but now that we have an open source model, no, we can look at each layer. We can look at the attention visualization itself. And I have a video about this if you want to know more. And I said, okay, so you did the fine-tuning here of only the LLM component in the VLM. So let's visualize now the attention maps. So we have a before and an after. Yeah? And Berkeley did this. Have a look at the paper. It's beautiful. There's a lot of more information. I just give you here the result. And it says, yes, the after maps of the attention visualization show us that finally the LLM, after the fine-tuning, and it's a very particular fine-tuning, the LLM has learned to attend directly to the relevant points of interest. And this means LLM in the VLM has finally learned to look where it needs to look at for its specific task, for its specific human query. Hallelujah. We finally found a way to tell the vision language model, you have to not to ignore, but to take into consideration the vision stream, the vision information that is coming into here. So you see, we have a problem. Now, let's talk about the experiment Berkeley did. And I have to tell you, this is problematic. This is a cause of critique from my side, because this architecture is simply too old. I'm sorry, I love Berkeley, but this is not okay. But there's a solution, never mind. So this is your original Berkeley, and they say, hey, for our VLM, we go with the prismatic, and you have here this and the vision backbone, beautiful, it's available on OpenClip or Team or wherever. So we know this, we work with this, I don't know, I have videos on this about 2 years ago. So these are known systems, no problem at all. Now each VLM in this particular configuration, it has to be simple, no? Berkeley does not have simply the money, at least not those students or those researchers here, to spend here really on big infrastructure. Okay, I understand this on an academic institution. So they have a vision backbone, they have a large language backbone based on a derivation from Llama, and the projector model. And as I told you, the simplest projector model is a 2-layer MLP. And then simple, no? You have a vision and a language component in the VLM, you freeze it, and then you start your training, and the projector is trained here on a Lava version 1.5 pre-training set. This is old. This is not up to current models, up to current status. But you have to understand why they did this. And I understand also the other point, because this is a controlled environment. Now, if you're not sure about the projector, it is very simply takes the output embeddings from the vision encoder and projects them into a different mathematical space, the LLM's embedding space. And since those spaces are not identical, it simply has to learn the projector, given here the pre-training dataset, to transform the visual features, in our vector space, into a specific format that the LLM can understand in its own mathematical space and process, just as if it was more text token. Great. So why they did this with the old infrastructure? Because this is more or less exactly 1 year old, and 1 year in AI is 10 years in the natural life. But there was this beautiful prismatic VLM publication, and I knew this, investigating here the design space of visually conditioned language model. And they provided here something of a controlled environment to really diagnose the problem. Open source model, and they could have a deep dive. And of course, a year ago, they went here with the version 1.5, state of the art at the time. And this is a beautiful reference benchmark. So I understand that you say, yeah, I go with something that I know, where we have all the reference values. I get it. But you know what's also nice, and this is maybe the quality of Berkeley, the authors of Berkeley anticipated here the criticism of my person here and said, okay, we understand this is an old architecture, so to counter this, they ran control experiment with more modern systems. Okay, so they established, hey, we're compatible, there's a coherence in our understanding with the old, 1 year old, experiment with the classical, let's say antique methodology from 2024. But we use here now more modern. No, it's a QN vision language model, a Phi3 vision, or an intern vision language model. So yeah, something that is at least in the same century. Great. And the result? The exact same trend holds. We get the exact same results. So it is not that these were the old models. No. Also those models show the same trends. And you say, damn it. So here you have in QNVL, Phi3 and the intern VL. And you see on all our vision-centric tasks, we get the same performance that we have seen here in this, what I called an old architecture. It is absolutely the same. And again, dotted, you have the pure random chance. If you have nothing, you just say, okay, let me guess here. I would go with 0.16. They are below. The vision language model here are below on all three of them, if you go for semantic correspondence, below a pure random chance, which is a catastrophe. Great. So what we learned from this study published by UC Berkeley yesterday, it tells us, hey, there's a lot of work to do. It is not to be negative about AI. It is not to say, my goodness, now the world breaks apart. No, it's just an opportunity to learn. There's a place for you if you want to do research in AI, because look at the problems we encounter. But it's also kind of a warning that tells us we need open source models. We need models that are free and open to everybody as an object where we can dissect here, go layer by layer, understand what is not working and further improve the system. Because those beautiful open AI global corporations or Anthropic corporation, they have to make money, and they would like to open here their system for your investigation. Because if you find out, hey, there's a problem, guess what the shareholders are doing, or guess what you understand the problem. So the research authors conclude, let's come to the end, that the primary failure mode of this vision language model on vision-centric task is not the quality of the vision encoders. Vision works. But it is simply our good old friend, the large language model, its inability to ground its reasoning. And my goodness, we are back to reasoning in large language model with the provided visual features. And you know what? This is so similar to one of my last videos where I was talking about this RAG multimedia non-performance. And if you go with MCP, if you go with A2A, whatever you do, and you know RAG is now purely agentic with multi-agent system and whatever, we had the same LLM inability. And now Berkeley tells us it is again the LLM inability to ground its reasoning in the provided visual features of the visual language transformer of the same AI system that we are talking about. So there is something. It's an indicator that something is not working as intended with our models. And it seems to be that the LLM still is here our prime mode of error. And this is fascinating because I have so many ideas how to further improve this, and you have ideas. And you know what? We have all the time and the place in the world to do this. So don't see it as a negative feature, but just as a chance to learn more. And hey, maybe you start a startup and you are able to solve some of those problems. No? So just to tell you, we have another beautiful major problems with large language models. And this is kind of great. So what is the takeaway? Vision language model. Stop confusing some VLM performance data with vision quality. All those rankings that you see are deceptive. No? Just to tell you, DINO version 2 for the spatial task here is great as a standalone solution, but it is not producing the best performance vision language model because we integrate it into systems. And interesting, if we integrate other part of the system in different ways, we can create asymmetric integration failures that you can read in the study. It's absolutely amazing what's going to happen, what's going wrong. But the bottleneck is the integration of multi-system components to a vision language model. No? It's just not building better vision encoders or LLMs in isolation. But if you really want to go multimodal, our system integration has to become better, and we do have a lot of work in front of us. And a word for benchmark. I know some of you wrote to me, but look at the benchmark. No, we are close to 99% performance. Yes, those benchmarks were created by companies that produce commercial VLMs. So guess what? Yeah. Be aware you should measure here a complex interplay of vision, language, and integration, and it would be great if the benchmark would give you performance indicator not just for the complete system, but also for parts of the system like the vision part, the language part, and if you want the bridging function, the integration part, how they come together. More about this in my next video. Because those benchmark results may not reflect here as much, for example, the pure capability of our vision encoder as much as we would like to believe. Because you know what? Our vision encoders are not bad at all. It is the large language model that are causing the main problem. So here we have the study UC Berkeley, UC Berkeley, UC Berkeley, and UC Berkeley. Okay, we are quite sure now which institution published this. This was published here on June 10th from June 9, 2025. And it's a beautiful paper. You know, and this paper also reveals a fundamental crack in the foundation of many popular vision language models, forcing here the community to look simply beyond the superficial benchmark scores. And you have to examine here in much more detail the harder problems of true, deep multimodal integration, because guess what? It's not working. Independent what global corporations try to sell you. Here's an example from this study from UC Berkeley where you have more of this beautiful example where it's failure, failure, failure. So in green, you have the ground truth. In red, you have the visual answer, but a purely visual answer. And in blue, you have the vision language model answer, the combined system answer. Yeah, and you see for example that it's not working. One of my viewers said, hey, what is the practical advice? Okay, you show us that there's something not working, but what I do now, what is the practical advice you give me? Now, this is a challenge. So I should go beyond the insights of UC Berkeley, and you think this is possible here in a free YouTube video? Yes, of course, you're right. So let's do this. Now, personally, I think for high-stake tasks, like medical image, where it's really absolutely important that you are 100% correct or close to 100%. Or just think about industrial defect detection, where I read that a lot of those production companies are switching over to AI. Do you really understand here the faults we have in our current vision language models? Autonomous navigation. I think currently you cannot absolutely rely on the final output of standard off-the-shelf VLMs. And I know you pay for them. But if you pay for them, is not a sign of quality. It is just that somebody makes money out of you. And I think the risk of our LLMs in those VLMs hallucinating, or simply, as I showed you here in this study by Berkeley, ignoring critical visual details, this risk is simply too high, and I think Berkeley demonstrated this beautifully. Of course, you can stay in your bubble and say, come on, nonsense. I love AI, I use AI, I do AI, but just be aware of the risk that you will encounter. As we have seen, there is some kind of way out. This is fine-tuning here, the vision language model. So if Berkeley told us, hey, if we did the fine-tuning here on the LLM component itself, using here a good model like a LoRa adapter model, great. But you know, careful, this fine-tuning data has to be very specific to your VLM. So I think, unproven, just my idea, the ideal fine-tuning data set has to have 3 characteristics. Like the task shown by Berkeley, it has to be evaluated against purely vision-centric task. Don't give the LLM any chance to interfere. It has to integrate vision-centric task. And then, yeah, of course, it has to break with the language biases, where I'm not really sure how to do this here in a simple way. But then the most important feature that you have to watch out is here. The training data for this particular fine-tuning on a VLM should be rich in task involving the geometry, the depth of the image or of the video, the texture-specific features, the correspondence and the object relation, the symmetries, and. So the demands here is spatial and structural reasoning capability of your training data to learn the VLM exactly what it is missing. Not easy, not currently done. If you have any ideas, hey, the comments here to my videos are open. So interesting. I try to build something for myself for a very particular niche domain in theoretical physics, but I think this is now interesting. And just to give you an idea, if you want additional information, I found this other paper from UC Berkeley published on the same day, June 9, 2025. Also absolutely fascinating. They talk here about the vision transformer. And there is also, if you want simple, is DINO version 2 perfect? And the answer is no. Because if you have a deep dive into the inner workings of DINO, you encounter here some particular tokens. And those particular tokens have here a concentration of high norm activation, and they call it outlier token. And guess what? They are leading here to an irregular attention pattern and a degrading downstream visual processing. So this regards also the standalone DINO version 2 and the integrated DINO version 2. But with DINO version 2, we already have above 80% performance. So if you just say about, hey, what I have to do first you have to fine-tune the LLM for the visual data. And then if you say, I want to improve here the visual performance of my DINO version 2, above 80%, then you should read this paper. And they have some beautiful idea. So you see, they're working on each and every little piece, every little corner of vision language model. And guess why they are working and focusing on this? Because they are not working perfectly. Okay, I think this is it for today. I hope you had a little bit of fun and AI is there to understand what is working, what is not working. And if I encounter a paradox in AI, like here, that the LLM in a VLM created here this paradox, I just love it because it gives me, and I hope the community, a beautiful chance to learn so much more about the inner working of the systems, how we can improve this system, and how we can build better applications. If you subscribe, I see you in my next video.